Oh, can you see my screen?
Yes.
Okay, good.
Yeah, I think we can go ahead. Welcome everyone to the ITP seminar, and today we have a talk by Yuya Kusuki, and he's going to talk about AdS BCFT from Bootstrap, construction of gravity with particle and brane. So please go ahead.
Yeah, thanks for giving me a chance to talk about my research here. Here I'd like to talk about the AdS BCFT from Bootstrap, from conformal Bootstrap equation, and how to construct statistical gravity with a particle and brane, following the facts from conformal Bootstrap equation. And this is based on a short paper and a little bit long paper with Yuya Way, a collaboration with Yuya. Okay. Let me first give an introduction of this talk. Okay, now main interest is boundary conformal AdS BCFT, which is the relation between boundary conformal field theory and AdS gravity with end of the world brane. And boundary conformal field, what's the boundary conformal field theory? And this is just the conformal field theory with a boundary. And here we impose a particular boundary condition called the Caudy boundary condition, and by using this Caudy boundary condition, actually we can apply the same word identity to evaluate a correlation function in boundary conformal field theory by using the mirror method. In other words, actually, we can evaluate the correlation function in boundary conformal field theory with the Caudy boundary condition in a similar way as the correlation function in the standard conformal field theory with the boundary. Oh yes, and here we focus on two-dimensional boundary conformal field theory and the three-dimensional AdS gravity within the world brane for simplicity.
Sorry, my ask questions. About this Caudy condition, does it mean that we are living on the half plane?
No, actually we can deform this boundary by using a conformal transformation. Actually here we impose the existence of a boundary breaks the part of a boundary conformal field conformal symmetry, but if we impose this part of conformal symmetry survives in this boundary conformal field theory, and so we can actually deform
by conformal map. So this
particular conformal map where this boundary condition satisfied in that
Does mean that we'll have just a half of full conformal symmetry.
Right. So here we have how to write something. In standard CFT, actually we have this conformal symmetry. We have this conformal symmetry, but in boundary conformal field theory, actually a part of conformal symmetry breaks down, but one of Virasol symmetry is survives.
Okay, it's just a diagonal, right? Embedded in the tensor product of two symmetry algebras.
Yeah.
Okay, thanks.
Yeah.
Sorry, what is the physical meaning of this condition, Caudy condition, and can it be extended to higher D?
The physical condition is that there's just the if we take for example, if we take the time direction like this, then actually this boundary condition means that just the
physically, it means that including a brane, you have less conformal symmetries than on a whole plane. Just a restriction. I mean, this Caudy condition.
Actually, the physical meaning of boundary conditions is simply that there is no energy loss. Yeah.
Okay, thank you. Yeah, this answers my question.
There's an interesting proposal about the holographic dual of boundary conformal field theory by Tadashi's paper and also Tadashi and Scrapar's paper. And they propose the bottom-up AdS BCFT model in that they propose their simplest, the minimal gravity that has a nice CFT dual with boundary. And this, that gravity is described by this Euclidean action in that the action, which has the Einstein-Hilbert action and massive particle, and also the given the Hawking term. And then the holographic dual is just given by something like this. In the here we have a boundary conformal field theory. Here we have a boundary conformal field theory, and here we have a boundary. Here we have boundary, and the holographic dual is given by gravity with end of the world brane that arises from this boundary. This. And here we impose and here we impose the Neumann boundary condition on this end of the world brane, like which can be described by this equation. And so that the configuration of this that the profile of this end of the world brane is dynamical, and which is the configuration of the end of the world brane is fixed by this equation, Neumann boundary condition. And so we can think of this guy as the Einstein equation of this brane. And so that's the reason why recent paper about the island model is some guy related about AdS BCFT to the island model. That's just a comment. This is now a setup. This is now a setup. And from and here I would like to give some issues of this gravity with a massive particle and end of the world brane. Okay, what is less understood in the gravity with end of the world brane and massive particle? There are three. Three that are not so well understood in this setup. The one is this brane self-intersection problem. I will explain it more details later. But anyway, here we have a massive particle. Maybe you can. I think this color is not so good. Here we have this is the end of the world brane. Actually, if we consider the global coordinate, then the holographic dual of boundary conformal field theory. This is the boundary conformal field theory, and the holographic dual of the boundary conformal field theory is given by like this. And here we have end of the world brane, and I describe this end of the world brane by this red line. But if we put a massive particle, in this geometry, then this end of the world brane is bound by the back reaction of this massive particle. And as a result, there's a possibility that the brane intersects with itself like this. It's a little bit strange. It seems to be strange. So we would like to understand. We would like to understand how to deal with this. Something like this self-intersection. But until this work, actually, there's no explanation for that. So we would like to address this issue in this setup. And the second issue is that the the definition of attention is this guy. The definition.
I'm sorry. Yeah, is it kind of horizon for a massive particle?
Sorry.
Is it a kind of horizon for a massive particle sitting inside the circle, red circle? In the case of self-intersecting brane on the previous slide, on the next slide.
This guy is just the conical defect, which is induced by this this term. Yeah, I will explain it. I will explain it later about this problem. Yeah. This is just here we put some matter on the brane. Yeah, and we call this guy as tension, and yeah, we can take the tension of the brane negative. We can set the tension of the brane negative, and as a result, what happens is that if we decrease the tension of the brane, then there's the possibility that part of this is the massive particle. This is the world line of the massive particle, and there's a possibility that a part of world line is hidden by the end of the world brane. And then there's we have we come up with natural question how to understand this world line behind the end of the world brane. And also yeah, this natural question. Yeah, it's obvious that if the disk one point function on a disk, should vanish if we consider non-scalar primary because of the rotational symmetry. But yeah, actually, it's not so obvious how to reproduce this property from the gravity side. In that, if we consider spinning particle, then this spinning particle should not interact with end of the world brane from this fact, from this CFT fact, but we don't know how to explain this property from the gravity side. Actually, the reason is just because actually there's it's a not so developed way to construct the gravity with a spinning particle. But yeah, here we give the solution to the gravity with massive particle and spinning particle, and then we give the explanation how to reproduce this property from the gravity side. The reason why this BCFT is not so well understood is just because for example, if we would like to discuss brane self-intersection, then we need to determine we need to know their profile of the end of the world brane. In other words, we need the details deep into the bulk. Unlike in a common case where we need only the information close to the asymptotic boundary. In other words, in common case, actually, we can evaluate various things by just using the Fifferman-Grafam expansion. But in this case, actually, we need the details deep into the bulk. So this is not the case. So in this case, actually, we need to solve the Einstein equation explicitly, but actually, this task is very difficult and very complicated. That's the reason why this BCFT or the profile of the brane is not so explored. And in this talk, we first address this issue by using the some CFT technique, in particular by using the conformal bootstrap. But the question is that how to address these issues from the CFT side. In other words, how to translate the problems into the language of the conformal bootstrap equation. Unfortunately, somehow the conformal bootstrap equation is not so explored in the context of the AdS BCFT, so there's a very limited know-how to apply bootstrap to address some issues in AdS BCFT. But here I give one example that the bootstrap equation is very useful to understand the AdS BCFT. The situation where the bootstrap equation is very useful. And the point is that, if we can succeed in translating some issues in gravity within the world brane particle into bootstrap problems, then actually we can easily give a robust, rigorous answer to those questions, right? No ambiguity to, by using the conformal bootstrap equation. Also, there's another issue that is not so well understood. In the actually from the conformal, from a CFT we can easily evaluate the entanglement, Renyi entanglement entropy in LDS BCFT in boundary conformal field theory. The entropy formula cannot reproduce this simple equation. In that, if we consider naive, if we apply the naive formula to evaluate the entanglement entropies, then actually we found somehow something like this term, something like this incorrect term, and so.
What is J?
G is the boundary entropy. It's just the disk partition function.
I is the unit operator. Right.
Sorry?
The average or the unit operator. A definition of J.
J. What is J? This is the identity. This is identity.
Identity. Okay. Mm-hmm.
Yeah. And the reason is the same in that, if we would like to reproduce this, oh, wait, I forgot the important part. Here we have log A over epsilon. And the reason is simple in that, in a similar way, actually, if we would like to reproduce this constant term, then we need the details deep into the bulk. Yeah, so that's the reason. Yeah, but in previous works about Renyi, holographic Renyi entropy, considering just consider this part, only this part, not without constant part. That's the reason why previous works about Renyi holographic Renyi entropy nicely works, but in this case it's it breaks down. In boundary conformal field theory, actually there is a new ingredient called the boundary primary, which is just a primary only lives only on boundary. I will explain the definition of boundary primary later. But anyway, so a natural question is, what's the holographic dual of boundary primary? And also, actually, there's no proof of this AdS BCFT that this model is naive and a bottom-up construction. So yeah, actually here I show some issues in gravity with end of the world brane massive particle. And so there's a possibility that, yeah, if we would like to resolve these problems, we need to refine this bottom-up construct, this bottom-up model in some way. But actually, as we will see in the talk, actually we don't need any modification, any refinement to resolve these problems. We don't need, yeah.
I'm sorry, one more question, please. When you say about boundary primary, do you mean primary living on the brane and not on a conformal boundary of AdS?
No, this is not brane. This lives only on the CFT boundary. So this is defined on boundary conformal field theory.
It's not a conformal boundary.
Well, for example, yeah. For example, let's consider something like yeah, if we would like to consider something like two different boundary conditions which are connected at some point, then actually here, yeah, this is yeah, here we need some boundary condition changing operator, and yeah, actually this is one example of boundary primary.
So sorry, I mean, I just misunderstood. So actually, you have two types of boundaries. The first, the standard boundary, is the conformal boundary for your AdS space. But also you have some kind of brane embedded in the AdS, which is another boundary. And in this way, you should consider two types of primaries living on conformal boundary on this surface.
So you mean
so that your safety just lives on the boundary of AdS space, right? But on its own turn, this CFT has its own boundary, some specific boundary condition. So by primary boundary primary, do you mean all primary operators living in your CFT, or just on this boundary line inside of two-dimensional surface?
This is just yeah, here, yeah, this this only lives on here, not end of the, yeah, not on the end of the world brane. This is this is defined on BCFT.
Okay, so this boundary primary lives on a one-dimensional line.
Yeah, this is this primary operator lives on one-dimensional boundary.
Okay.
Yeah, I will explain details. Yeah, about the definition of the boundary primary later.
Mm-hmm.
And this is a short summary of this talk. Yeah. In the first part, actually, I address issues by using the conformal bootstrap equation. And this approach tells us a rigorous answer about how to understand all these issues. I mean, yeah, we address this question. We address these questions by using the conformal bootstrap equation. And then now we have the mechanism of how to resolve these problems. And the natural question is how to reproduce this mechanism from the gravity side. And then to answer this question, we developed a simple way to construct a gravity with the end of the world brane particle. I mean, if we would like to do it, then in general, we need to solve the Einstein equation explicitly. But sometimes actually we don't need to do it. Actually, we can take an alternative way to give the solution to the Einstein equation, and we give this alternative way to construct gravity with the end of the world brane particle. And then this solution tells us how to resolve this problems from the gravity side. And this result is completely consistent. Yeah, completely reproduces the Bootstrap results. In that here in the second part we overcome this problem. And in the third part, actually, I would like to give the define the formula of the holographic linear entropy, but actually I don't have enough time to explain it, so maybe I will skip this part. But if you are interested in this part, then please ask me after this talk. And here we can also give the gravity dual boundary primary. And I would like to emphasize that actually everything is consistent. So it implies that the bottom-up AdS BCFT nicely works without any refinements. Okay, so from now on, I will give these topics. This is a short summary of this talk. And so we first address these issues by using the conformal bootstrap equation, and then we also address this issue from gravity side. And for this purpose, we give a way to construct gravity with end of the world brane particle. And actually, I would like to comment that actually there are many loopholes in gravity calculation in this setup. For example, identification of ADM mass and conformal dimension, and also the difference between boundary primary and bulk primary. So actually, for this reason, there are some papers. That use incorrect identification between ADM mass and conformal dimension and gives the incorrect answer. So we should be careful. But now, fortunately, actually now we already know the concrete answer for our problems. For the gravity with the end of the world brane. So actually, we can say that now construction of gravity with the end of the world brane particle is completely correct, and which is consistent with the conformal field theory. Okay. And from now, I will give the details of my result. And let me first give a review of boundary conformal field theory. In boundary conformal field theory, actually we have additional ingredient called boundary primary, which is a primary operator living on boundary, and which can, for example, change the boundary condition. But actually, this follows the same transformation law under the conformal mapping. And in this talk, actually, I will describe the boundary primary by boundary primary by 5 wheels capital I and capital K letter, and on the other hand, I will describe a bulk primary by 5 wheels lowercase indices. Oh yeah, something like that. Yeah, the boundary primary. Yeah, for example, you can find this boundary primary as the boundary condition changing operator, and also you can find this boundary primary in the OPE, in the bulk boundary OPE. And yeah, we can easily evaluate the conformal dimension with this boundary primary in that yeah, we can consider a state operator like mapping for this CFT with boundary. And so the conformal weight of boundary primary is just given by the energy correspond to this state on this strip with 2 different boundary condition A and B. And if we would like to evaluate correlation function, if we would like to evaluate the correlation function, then yeah, in conformal field theory, what we do generally is cut. Yeah, what we do is just the punch decomposition like this, in that for example, if we would like to evaluate 2-point function, if we would like to evaluate a 2-point function on a disk, then yeah, what we need to do is to cut this 2-point function on the disk along this line, or equivalently here what I did is just to insert a complete sets along this line, and here we take the if we would like to do it, then here we take the time direction like this, and then we can express this 2-point function on disk as just a sum of just something like this summation. And maybe you know, yeah, this is called the OPE coefficient. This is called the OPE coefficients. And the point is that in this expression, actually, the dynamical part and the kinematic part is completely decomposing in the. This function is just a special function like the hypergeometric function. This function is completely fixed by conformal symmetry and mirror method, and this is called maybe you know, this is called the conformal block or the Virasoro block in 2-dimensional quantum conformal field theory. And so if we would like to evaluate any correlation function in BCFT, then what we need to know is just the coupling constant. And this is a comment that actually this function is the standard Virasoro block, because as I mentioned before, by using the mirror method, the word identity, in this boundary conformal field theory is completely equivalent to the standard word identity in conformal field theory with boundary.
I'm sorry, may I ask again? So, is it correct to think about this 2-point function with this kind of conformal block? Is that in order to calculate two-point function and boundary CFT, we actually need to calculate four-point function in the standard CFT. This is why we current here the conformal block function in this sum.
Here what happens is that maybe it would be better.
Does it mean that using this mirror method instead of two operators, we should consider four operators?
Yeah, more precisely, actually, this has a chiral part and anti-chiral part, but by using the mirror method, then this can be translated. This can be re-expressed in terms of a four-point function with chiral part of this primary operator I and anti-chiral part of this primary I.
Yeah. Okay. And one more question about this first coefficient CPO in the first formula. Usually we understand the structure constants as three-point functions, and this is correct for the second coefficient, but the first coefficient contains just two indices. Is it related to the two-point function?
You mean this guy?
Yes.
In boundary, actually, maybe in conformal field theory without boundary, actually we can completely fix the correlation function with central charge and OP coefficients. But in boundary conformal field theory, there are additional we need additional information in that. Besides bulk OPE coefficients, we also need the information about this is bulk.
And this is the standard OPE, right? Bulk.
I mean, in boundary conformal field theory, actually in standard CFT, actually we only have this guy and central charge, but in boundary conformal field theory, we also have bulk boundary OPE coefficients and boundary OPE coefficients, which can be described in something like this. In that bulk boundary OP coefficients is just the two-point function like this, but by using the mirror method, actually this is equivalent to something like three-point function like this. So actually we cannot fix this guy by using the conformal symmetry. This is dynamical one, and also this is also dynamical one. So we can't fix this guy by using the conformal symmetry.
Yeah, but it's a bit strange because in the standard OPE, we should multiply two operators to obtain the third operator. And this is how we obtain the structure constant with three indices, right? But in this case, what we're going to do, we need to take just one operator and expand it in terms of other operators. You see that three indices in the standard case, bulk, I and J are for the operators on the left-hand side, and K for the operator on the right-hand side. But when you consider bulk boundary, what does it mean from the OPE perspective? We should take two operators and expand this product in terms of the different set of, say, primary operators of conformal families.
Sorry, let me clarify your question.
I mean that OPE usually involves three operators. Two operators are multiplied on the left-hand side, and the third operator is just the extension coefficient on the right-hand side. But when you say about OPE for
Here we just consider the OPE between I and J. In that here we consider the OPE between CIP and then like this guy. Then actually we should also find something like a one-point function of this guy. I mean, yeah, here what I consider is something like this in that OI or J to CIJ.
So CPO is just CPPO, just a notation, shorthand notation, right? For 3 operators, and 2 operators of them are identical.
Here, what we consider is something like this decomposition that OI and OJ can be expanded into CIJP times primary operator OP, but here we consider this, and so the summation should be described by something like this, and we express this guy just CIP. CPC, no, CPI.
PPI. Okay, okay.
Where am I? Oh yeah. What I say? Oh yeah. Yeah. Actually, this and yeah. Here we consider boundary conformal field theory. So you may wonder if this is yeah. What is this? What is this? And yeah. Actually, this is just a standard Virasol block for a 4-point function on a sphere by using and we can naively understand this relation by using the mirror method, but we can directly check it by just an brute calculation like this. In that yeah, here we use the mirror method, and then this is just a 2-point function, so this is something like a Kronecker delta, and so as a result we obtain the standard Virasol block like this. And then yeah, I already explained it, but yeah, anyway, so if we now we have boundary. So yeah, the existence of a boundary is the new coupling constant for called the bulk boundary OBE coefficients. So I mean, if we would like to evaluate some correlation function with boundaries, then we need additional information. Maybe you wonder if there's another way of how to count, like this. In that we can do it. And yeah, in that here what we consider is just the without boundary operator complete set, or equivalently here what I did is just to use the bulk boundary OPE like this. And by using the bulk boundary OPE, then actually we can give another expression for the same correlation function like this. In that we can re-express a 2-point function on the disk by just using the product of sum over Virasol blocks with the product with the product of bulk boundary OPE coefficient like this.
Sorry, I still don't understand why do you call this OPE, operator product expansion? Because on the left-hand side you have just one operator, and then you represent this operator as a particular sum.
Actually, here what I consider is something like that. Yeah, you are right. Here we only have one operator, but yeah, here we have boundary. So yeah, actually we can think of this guys is something like 2-point function by using the mirror method. And we call, yeah, roughly speaking, this is this OPE is something like an OPE between this primary operator and its mirror.
I see now. Okay.
Yeah.
Okay.
So sorry, does that mean that like any operator in the bulk can be expanded into operators on the boundary?
Right.
But why would you study then, I don't know, correlators of operators in the bulk if everything can be expressed in terms of the boundary? I don't know, isn't that redundant then? Like, I would say that then this implies that everything reduces to CFT on the boundary.
It is kind of AdS CFT.
Yeah, yeah.
Including local degrees of freedom in terms of boundary degrees of freedom.
Yeah. Oh, can I continue?
Yeah, okay, go ahead, yeah.
Yeah. And then I would like to explain what is the conformal bootstrap equation. Yeah, this is the most standard bootstrap equation. That the bootstrap equation for 4-point function on the sphere. I mean, yeah, before explaining about the bootstrap equation in boundary conformal field theory, I would like to give the warm-up of the bootstrap equation. Yeah, actually for a 4-point function sphere, we have 2 ways of how to count, like this one, like this, and as a result, we obtain 2 expressions like this. In that, in this case, we take this time direction. In this case, actually, we take this time direction. And so from the path integral picture, actually, this equality is a little bit trivial, but yeah, in the radial quantization, actually, it's a little bit non-trivial. And yeah, as you can see here, actually, this is a non-trivial equation in that we can, in the radial quantization, actually, we can give 2 different expressions from the same 4-point function. And this is the consistency condition in conformal field theory. And this is called the conformal bootstrap equation. And by using this equation, we can give some constraints on this OPE coefficients and the spectrum. And this is just a special function. This is just a special function. So yeah, we already know what's this guy. And this is one example of the application of the bootstrap equation to give the universal formula for the OPE coefficients. Okay, this is just a bootstrap equation, but yeah. Sometimes we can, in general, actually, it's very hard to solve the bootstrap equation. It's very hard to solve the bootstrap equation, but sometimes we can approximate sum of correlation function by just a single block for one of these 2 channels. Like this. So for example, in the high temperature limit or in the large spin limit, actually we can approximate this for a summation by just the vacuum block. Yeah, we can sometimes feel this vacuum block approximation in the derivation of the Cardi formula or something like that. But this is the more this is the current way to solve the Bootstrap equation. Yeah, this is a new way to solve the Bootstrap equation. In that, if we can approximate one of these channels by just the vacuum block, then yeah, actually it's the integral transformation of the Virasol block has already been studied, and we already know the integral transformation like this. In that, this is the transformation between from the one channel to the dual channel, like this. And also, yeah, fortunately, we already know the explicit form of this the kernel of this integral transformation. And this transformation is called the fusion transformation. And now, yeah.
Is it the same as 6J symbols?
Sorry?
You know, like, is it the same as 6J symbols?
Yeah, right. Yeah.
Okay.
And let's go back this channel. Then this channel is expressed by like this. And oh, now, yeah, actually, these two guys is expressed here in terms of the same basis. Oh, I forgot the square. So actually, by the coefficient comparison between these two equations, we can fix this OPE coefficients in that. From this Bootstrap equation, we can fix the OPE coefficients by just this fusion transformation. And for example, by applying this approach to a torus partition function, then actually we can say that the density of states is just given by modular matrix, which is an analog of this fusion kernel, and actually this completely reproduces the Carty form. And this is a little bit generalization of this approach. Yeah, this guy. And then actually by using this method, actually we can give the universal formula for the OPE coefficients in the high energy region. It's already studied. For example, bulk OPE coefficients in this paper, and bulk boundary OPE coefficients, boundary OPE coefficients is studied in these two papers. Yeah, like this. Yeah, this is the known result from the analytic bootstrap in two-dimensional conformal field theory. And we would like to apply this approach to understand the AdS BCFT. Yeah, from now I would like to bootstrap AdS BCFT. Yeah, now
sorry, 1 second. I just wanted to warn you that like we have 6 minutes till the official end of the seminar. It can be extended like with 15 minutes, but just like to let you know, okay?
Yeah. Oh, it's already. I see.
Yeah. Yes. Yes. So.
Okay. Let me. Yeah.
Yeah. So you may have like 15 minutes or maybe something like that.
Okay. Okay. Yeah. Okay. No problem. Yeah, here I'd like to bootstrap the AdS BCFT. And yeah, as I mentioned before, if we have a heavy particle, and then the back reaction bends the end of the world brane, and so Yeah, actually, we know the relation between massive particle and conformal dimension. And so, yeah, actually, we can fix the profile of the end of the world brane. And then, yeah, we can show that if the conformal dimension is larger than C over 32, then actually this self-intersection happens. And this has already been pointed out by some papers. And so, for example, the first paper proposed that the primary operators in this regime should be excluded in the holographic CFT. But it seems to be a little bit strange. So yeah, I would like to address this issue by using the conformal bootstrap equation to give a robust answer for this problem. Yeah. And yeah, now setup is something like that in that yeah, to induce a conical defect from massive particles, and here we put bulk primary. And so yeah, actually here on the CFT side here, what we consider is a 2-point function on the disk. Yeah, here this is the boundary of CFT. And now our interest is the energy of this gravity, in that our interest is the ADM mass. And I'd like to emphasize that yeah, this ADM mass is not equal to the mass which appears in the action. In that this M is the mass, rest mass of this particle. But this is not equal to the ADM mass, because here we have a non-trivial gravitational interaction. Yeah, and to solve the bootstrap equation, we need some input. And what's the input? And the input is yeah, actually here we assume, yeah, we implicitly assume that there's no matter propagation between this world line and the end of the world brane. There's no interaction between particles and brane except for gravitons. Yeah, this is already pointed out in some papers. And yeah, we can translate this condition in the CFT language. And in the CFT language, actually, this means that 1-point function. Yeah, right. 1-point function on disk should vanish except for vacuum. And actually, this condition can be realized, for example, if we consider this case P equal P not equal P bar. Well, and so let's solve the bootstrap equation in some by using this assumption. Yeah, this is just a bootstrap equation for 2-point function on the disk. And here you can see 1-point function on the disk, and so we can use the assumption for this for this channel, and then we can so this summation can be replaced by just the vacuum, and so we can apply the same approach as I mentioned before for this problem. In that, what we need to do is just apply the actual fusion transformation to this vacuum Virasoro block, and then we can extract the information about the spectrum of this P by using this fusion matrix. And then actually we can conclude that the ADM mass is just given by, actually we can give the spectrum of this guy, but what we are interested in is the solution to the Einstein equation, in that just a classical solution. So we are now interested in only the lowest conformal dimension that appears in this in this summation, and actually it's just so we can identify the ADM mass is just given by the lower conformal dimension of this in this summation. It's given by 2 alpha I. The I and this I is the Liouville momentum here defined by this.
I'm sorry. sorry, may I ask you? So usually ADM mass is assigned to a particular gravitational configuration. And which configuration of graviton fields do you consider?
Here we consider global coordinate and the length of the asymptotic boundary is given by pi. Yeah, we consider this configuration.
Mm-hmm.
Yeah, actually, this is the conventional configuration for if we would like to relate the conformal dimension to the ADM mass, then we need to consider something like this configuration, because as you pointed out, the ADM mass is not scalar.
Okay.
Anyway, so actually the energy of this geometry is not just given by the mass of a particle, but given by given by a little bit non-trivial, in that the medium mass is given by 2 alpha I q minus 2 alpha I. So it implies that actually the black hole forms when the mass of a particle is larger than c over 32, not c over 24, not c over 24. And so actually this this bound, this threshold completely matches the self-intersection bound that, as I mentioned before, in that the c over 32 also appears here. So it implies that actually the self-intersection can be avoided by black hole formation. And actually, we can generate this result to spinning particle. And the point is that actually the solution to this Bootstrap equation is not sensitive to tension of the brane. So actually in previous paper, it has been pointed out that as you can see in gravity side, if we consider negative tension, then the solution to the Einstein equation seems to have some transition, because in that case actually the brane attaches world line, but actually such a transition should not happen, because the solution from the conformal Bootstrap equation, we cannot find such a transition from the conformal Bootstrap equation. Well, I will quickly explain how to construct the gravity dual of this geometry. Actually, maybe we have a simple way to construct the gravity with a conical defect. Here we consider not gravity without brane. And what we need to do is just count and paste. And then we can obtain the gravity with conical defect. And then actually this procedure can reproduce the ADM mass. But here we should be careful. Because as I mentioned before, ADM mass is not a scalar, so we should consider an appropriate coordinate to identify the ADM mass and to the conformal dimension. So that's the reason why we consider the rescale like this. In that, if we cut this guy, then actually the circumference of the asymptotic boundary is a little bit shrunk. But but if we would like to relate the conformal dimension to the ADM mass, then we need to rescale this guy like this. Yeah, actually, the same approach can be applied to the to the case with a boundary with the end of the world brane. Actually, in that case, the circumference of the asymptotic boundary is more shrunk like this. So for example, the coefficient of this risk error parameter is a little bit challenged, but actually this nicely works. And finally, we obtain this ADM mass. And the point is that this ADM mass is different from just the 2HI, but this is reasonable because, as I mentioned before, actually this conical defect. Here we have non-trivial gravitational interaction between conical defect of the end of the world brane. So ADM mass is not equal to just the mass of a particle. And actually this, and by using this construction, actually we can show that the ADM mass is not given by just the mass of a particle, but this guy. And the point, and actually this ADM mass completely matches the CFT conformal bootstrap equation in that as I mentioned before, the relation between the ADM mass and the mass of a particle is given by this guy, and this completely matches this guy. And so so I can argue that this construction is completely correct, consistent with the conformal bootstrap equation. I don't have enough time to explain the spinning particle case, so let me skip. Which part should I skip? Actually, in a similar way, we can give the twist, spinning defect geometry. In that, I don't have enough time to explain the details, but what we need to consider is just something like this twisted identification. And by using this guy, then actually we can construct the geometry with a spinning particle, and then we can explain why the spinning particle cannot interact with the brane, because this twisted identification risks the mismatch of brane. And so, such singular configuration is not the solution. So, then, so this construction can explain why the one-point function disk should vanish. Okay, let me skip other parts. Let me skip other parts, and so wait. And this is the discussion. And so, as a future work, actually there are many, there seems to be many applications of this setup in that maybe we can consider more other bootstrap equation in AdS BCFT. And also here we give a construction of geometry with a spinning particle, and so maybe this can be applied to study more various setups, including spinning particles, and also we may be able to consider wormholes in this BCFT, and maybe we can give some insights into brane world holography. And it would be interesting to consider higher dimensional generalization. That's all. Thank you.
Okay, thank you. Are there any questions? Okay. Oh no, it's not a question. Okay, so I have a question. So I'm like comparing to the usual bootstrap without any boundaries. So usually what they get is some kind of island, some kind of limits, but you immediately got an exact formula. How does it work? Like, because you have too many free like coefficients to fix, the only thing that you know that like some of them are positive. Right?
You mean you ask the reason why this is I can give the exact solution to the Bootstrap equation in this case.
Yes, yes.
This is just because yeah, here we have input data. Here we have input data like this. Yeah, this is very strong. This is very strong assumption. Actually, more precisely, actually, this holds only one of C. In that, yeah, this holds only in the large C limit. But anyway, yeah, and yeah, this is very strong enough to replace this summation by just the vacuum block. In that, in general, actually, if we would like to approximate the sum of this sum by single block, we need to consider, for example, some limit, blah blah blah. But here now, actually, we have a very strong constraint like this. Yeah. So actually, without any limits, actually, we can give this vacuum. We can re-express this two-point function of disk by just a vacuum block. So the answer is simple in that we have in the AdS BCFT context, we have a very strong condition to solve the Bootstrap equation.
Okay, another question. So okay, I'm not very knowledgeable about this, but what happens if you just, I don't know, consider a simple case, no particles in the bulk, no branes, just gravity. So what's the CFT dual?
You mean the CFT dual of this guy?
Of pure gravity.
Of pure gravity.
Yeah, I mean, no particles, no branes.
No particle and no branes. Oh, sorry, what's the question?
So what's the CFT dual?
I see. Actually, we don't know. You mean, yeah. Actually, we know that the holographic, CFT dual of pure gravity should have something like this property, and spectrum should be has a very large gap. Yeah, large gap. We know these two properties, but we don't know the explicit form of, for example, spectrum or OPE coefficients. Yeah, if we already know that, guys, then we don't need to solve the Bootstrap equation. But we don't know that information. So in various works, we solve the Bootstrap equation by using these few assumptions, and we pick up a part of information about the holographic CFT.
So here you're essentially solving a more complicated problem where, like, in which you add some extra stuff in the bulk, right? And even despite your limited knowledge about the CFT, you still can proceed because, like, you make some assumptions, limits, right?
But I mean, if we would like to find the CFT dual of the gravity, then actually we need some input from the gravity side. And in this case, I just say that the input from the gravity side is given by is just this guy. And then we can partly solve the Bootstrap equation. So we can we give the information about the we partly give the information about the OP coefficients in that. In this case, actually, the OPE coefficients is not squared. It's just given by fusion matrix. So we can partly give the information about this holographic CFT, but here I don't fix all of OP coefficients. Yeah, there are still many unknown OP coefficients in this setup.
Mm-hmm. Okay, thank you. Any other questions? Okay, if no, let me thank the speaker.
Thank you. Yeah.
Thank you. And to everyone, see you next time.